and scalar multiplication. All right? Which you can't really check me on because I haven't given you a proper definition of the wedge product, so you have to take me at face value that this is in fact true if we were to define it properly. So sorry. I don't know if there's, and I'm not sure if you go looking in Rentelen, you're going to really find it there either. He is very, very sneaky about just doing things. He doesn't define everything in there. If you want to see everything defined, you can look at, for example, Jeff Reilly's book or John Lee's book. These, okay, anyway, so listen, we're trying to work our way to beta wedge alpha, all right? So these are just numbers. So they commute. So, and these are finite sums, so they can be flipped. Because, you know, you can prove that by induction in Math 200. If you want. I mean, I want to. Not like this, but. All right. Now the problem at this point, let me write it out, is that we're up against EI1 wedge, EI2 wedge, dot, 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 wedge, EI. How many I's are there? P of them. Right? And then we're wedging with EJ1, wedgie, 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 EJQ. It's an easy audience. Let's see here. So, what does it cost me to bring this guy, right? I want to bring that all the way over to here. What'd you say? -1. So I have flip number 1, flip number 2. How many flips? It costs, yes, P. P flips, which each one gives me a -1. Yes, I get -1 to the P. All right? Then I would have EJ1 wedged with, I'm just going to write it as EI if you guys don't mind, wedged with EJ2, wedge, dot, dot, wedge, EJQ, right? How many does it cost me to bring this one over to, well, I don't want to bring it over to there. I wanted to bring it over to here. I have to go past how many? P, P dual vectors, PE upper I. So again, it's P flips. It's P flips again. So I get, I'm running out of board space here, so if you don't mind, I'm going to get to the point. J and IQ, the sum over I and IP. We have beta sub j, alpha sub I, -1 to the p, -1 to the p. How many of these? -1 to the p. Apparently, q-fold of those. And that leaves me with EJ, wedge, EI. It's what? Yeah.
So some of your I's, so EI1 in some cases, or EI1 is equal to EJ something, for instance, right?
Could be.
So what?
I don't care though.
Those would be 0.
Those would be 0, but it's still fine. Yes.
Does that simplify the what negative q to the p, or am I just?
Oh yeah. So that we can factor out. That gives us a -1 to the PQ. And then we've got a sum over J in IQ of beta J, E upper J, wedged with the sum over I in IP of alpha I, E upper I, which is minus 1 to the PQ beta wedge alpha, which is what we were trying to show. Yeah? Does that show enough detail for it to make sense? I mean, we could add more detail. This is really the main event, is the flipping the wedges there. That's where everything is. And you're absolutely right, Sam. They could be 0. I have a notation for all this, which is EI wedge EJ is epsilon IJ EIJ, like that. What I mean by that is I take the multi-index I take the multi-index J, and I put them in order. So if there's any repeat, that epsilon symbol is 0. And otherwise, it's the necessary plus or minus to put the EI1 through EIP and the EJ1 through EJQ into order. So it's either that epsilon symbol is either plus, minus, or... Let me just show you how it works. So like, if I was to say, for example, take E1, E13 wedged with E25, so I would have epsilon, 1, 3, 2, 5 in my silly notation, and then E. All right, so what I mean by that is E1 wedge E2 wedge E3 wedge E5, and this would be what? I'm not sure we even need this notation, but if we ask the wrong question in homework, maybe it'd be helpful to you guys to have it. I don't know. I've used this notation sometimes if I ask the wrong question of myself. So you see how this goes? In order to get from this, right? Why is this not desirable? This is not desirable because it's not a basis form. If we're using our basis to be like increasing indices, it's not in the right order. So all I need to do is to flip the 2 and the 3, right? So this is just minus 1. That's by construction. On the other hand, if I took the wedge product of two multi things that had a matching indice, that'd just be 0. Yeah. All right, so what is the wedge product of any one form in itself?
That would be a 0.
0. And are you sure?
Yeah, A dot A is the same way.
No, I mean, like, why is alpha wedge alpha?
Because alpha wedge alpha equals negative alpha wedge alpha.
Oh, okay. So theorem, if alpha is one form, then alpha wedge alpha is minus 1 to the 1 times 1 alpha wedge alpha, right? Which is minus alpha wedge alpha. Therefore, alpha wedge alpha is equal to 0. I'll believe that. Very good. But you see, that's a corollary to what we just proved. Right? Yeah?
You can also break it up into the tensor.
Oh, very good. Yes, we could also rely on our tensor product. Very good point. That's another way to prove this directly. But my point is we also can prove it if we, okay, so like, if you can imagine yourself in a world where we don't have the tensor product stuff, we just have the algebraic properties of the wedge product, like we talked about today, we could still prove this without knowing that it's the tensor product. But that's kind of the rub with the two viewpoints I was talking about at the start of class. the tensor product viewpoint allows us to concretely prove things going back to the tensor product formulas, whereas this other viewpoint, which I'm not entirely defining. Okay, anyway, so another theorem, if we have V1, V2, Vk, a linearly dependent set of vectors, then V1 wedge V2 wedge wedge Vk is equal to 0. So you might notice I pulled a fast one on you. I've just extended the notion of wedge product to vectors. I hope that's okay. If you'd like, we could make these forms. Would that be better? We could make them forms. Alpha 1, alpha 2, alpha k, a linearly dependent set of 1 forms, then alpha 1 wedge alpha 2 wedge wedge alpha k must be 0. I'm trying to remember, is this an if and only if, or is this a... This is an if then. If then. All right. So how does the proof look like? To say that that's a linearly dependent set of 1 forms, yeah.
Is it vector or 1 form?
No. Not necessarily. I mean, but we could still talk about the wedge product of vectors that would give us... People typically call those multi-vectors. But in the same way you can construct the wedge product of 2 forms to get a 2 form, you can talk about the wedge product of 2 vectors to get what's called a 2 vector. So, yeah. It would have all the same algebraic properties we talked about. Like there would be 2 to the n multi-vectors over Rn, just the same. But I focus primarily on P forms in here, because ultimately we'll see that there's a calculus of differential forms, which is very natural. There's no, as far as I know, nice calculus for multi-vector fields. But anyway, I'm getting ahead of the story a little bit. But so here, if it's a linearly dependent set of forms, that means that we can write one of them as a linear combination of the rest, right? So that means that there has to, we can say alpha j is equal to a sum I not equal to j, right, of ci alpha I, right? And then if we look at, alpha 1 wedge alpha 2 wedge wedge alpha j wedge alpha k, that is alpha 1 wedge alpha 2, and then we've got, of course, our summation I not equal to j of ci alpha I. But then by the properties of the wedge product, namely that it's distributive across addition, I can pull that summation out front. I can pull the constant out front. And I'd have like plus or minus alpha 1 wedge alpha I wedge alpha I. If you'll allow me this very sloppy notation. My point is, for every one of these sums, right? You can pull the I that's this I, every one of these is somewhere else in this wedge product, right? For example, if I is equal to 1, it's over here. So I can go duke, 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 and bring it over to there. It costs me a plus or a minus, depending on if it's an even or an odd number of flips. But at the end, I've got alpha I wedge alpha I here, right? If I was equal to n, I can bring it from here over to here. So, I mean, this notation with understanding. The point is, you can rearrange them so that you have a repeated that, right? Which is what? By our previous theorem, 0, which makes all of this 0, because by the way, one of the properties of the wedge product is the wedge product of 0 with anything is 0. That follows from distributivity, right? Like if I have alpha wedge 0, that's alpha wedge 0 plus 0, which is alpha wedge 0 plus alpha wedge 0. So therefore alpha wedge 0 is, well, 0. You might recognize this argument. It's the same argument I gave you to show you the linear transformation acting on 0 is 0. It's the same stupid argument. The wedge product of 0 is 0. Follows from distributivity. So this is kind of neat. This means that the wedge product is a way of detecting linear dependence. If the wedge product of K1 forms is 0, that means there's a linear dependence amongst the 1 forms. Right? In fact, if they're not equal, if the wedge product of K1 forms is not equal to 0, it means that they're linearly independent. That is also true. All right.
Mission 8 changed my life.
Mission 8 changed your life.
I'm not joking, it really did.
All right, I think I have like one more thing to show you guys and we're done for today. I really should show you this today because these patterns we've been knee deep in today, if I try to come back to them next time, it won't make as much sense to you then. So let's just get it over with here. I hear some kind of, what's that about? Oh, this is some sort of the sky is falling, nothing makes sense comment. I guess I'll allow it. All right, computer, come on. What? What was that?
It's a thermometer.
This is a silly place. All right, so some of you have had my 321. In 321, I've been using the wedge product as a means to define the determinant. And so like we played around with the wedge product as a means of understanding the determinant. Here, it's the other way around because we've defined the wedge product with a tensor product. So I can use the wedge product to build determinant formulas, you see? As I do eventually here. It's not nasty. These formulas are beautiful. There's much more detail on the alpha wedge beta calculation in the notes, right? You might wonder, why is that a homework problem? Well, because I'd like you to understand it. So you're like, so you mean you assigned me a homework problem where you have the solution in the notes and you went over it in class? Yeah, that happened, yep.
Type all these in LaTeX.
Yes, I did.
I don't envy you.
I enjoy it. So
Okay.
here is the two-dimensional 2x2 matrix, and you can write the the determinant of the 2x2 matrix as like the wedge product of E1 with E2 acting on column 1 of that matrix and then column 2 of that matrix. I've just A1 is AC, A2 is BC, and if you just feed that to the tensor product, out pops the determinant. So we could use the wedge product to define the determinant if we wanted to, because the wedge product is completely antisymmetric, and that's what the determinant is. It's a completely antisymmetric function of its columns. Here is the 3x3 determinant, which would be E1 wedge E2 wedge E3 acting on 3 columns. That gives us many more terms, and if you regroup them, you can see what you have is that, and you can actually sort through these things and discover like cofactor expansions by regrouping the wedge product if you look at it. Like here, I just did the wedge product of this 3 by 3 matrix, and using the identity I had in the previous page, out pops this, which you might recognize as like I think this is the Laplace expansion by minors on the first column. The A, the minus D, the G, that's like EF, HI. But anyway, so yeah, just a comment. The other way to do this, and you'll see this in some books, here's a token calculation. Here's the proof that omega wedge, like we did this without the benefit of cool index junk today, but see here, I have this wedge that. What I did was, I guess I'm done for today. Let me stop. Energy leaving me. So next time, we'll talk about Hodge duality and the musical morphisms, I think. So, yep.